Hello and welcome to our presentation today. My name is Kelly Dunn and I will be your presenter. Today I will be presenting on the topic of seismic suppressors, and we will go through a comparison of base isolators, shear walls, and fluid viscous dampers. Out here in California where I live, earthquakes are kind of a big deal, especially when designing a building. There are several fault lines around, and so you really need to have a good idea of seismic design when you are going to design a building. Earthquakes obviously are just a natural hazard. There's nothing we can do to avoid them, really. They've been around as long as the Earth's been around, pretty much. The earliest recorded earthquake in China was recorded in 1177 BC. In Europe was recorded in 580 BC. An earthquake basically is when the tectonic plates of the Earth, which are all situated next to each other, either they shift laterally, so they slide next to each other, causing friction and causing the Earth to shake, or sometimes the plates try to squeeze under one another or over, one's going up, one's going down, and that also causes friction, causes earthquakes, causes damage most of the time. Damage from earthquakes can be intense or it can be little. Magnitude doesn't always have to do everything with how much damage occurs, especially in more modern cities where earthquake design has been taken into account and buildings are ready for it. The largest recorded earthquake was a 9.5 on the Richter scale, which is the most common scale used. This occurred in Chile in 1960, but again, magnitude isn't the main factor in everything. Population density of where the epicenter of the earthquake is probably the biggest factor. How many buildings there are, obviously the more buildings, the higher probability that there will be damage from the earthquake. So let's get into the presentation now. The first type of seismic suppressor I'd like to talk about are known as base isolators. And here I have a diagram of the most basic type. Basically, a base isolator are layers of rubber sheets piled on top of each other. And in this example, there is a lead plug in the middle of it just to help stiffen it. During an earthquake, the ground shakes horizontally, obviously, and the rubber isolators are able to move horizontally and to take all that energy into a horizontal motion and not transfer any vertically, so that your building will stay straight like this and just move, and nothing bad will happen to it, hopefully. In this next diagram, I know it's hard to see, sorry about that. This is a fixed base building, and then this is an isolated building. It just has base isolators right under the frame here. This one has none. And during an earthquake, the ground movement is that way. You can see this building tilts, and this is no longer a 90-degree angle here in these corners. But the isolated building, the base isolators tilt, basically, and the frame stays square, causing much, much less damage during an earthquake. Base isolators are ideal for shorter buildings, not so much for skyscrapers and things such as that, but they work well for large buildings such as warehouses or large office buildings, schools, things like that. They're ideal for that. Bearings can be incorporated into the initial design, or oftentimes buildings can be retrofitted with the bearings, so either way. They're generally low cost, they're pretty easy to manufacture, and so these are just a good idea for any building that you want to be seismically sound. However, the isolators can only be used on certain types of soil. For sandy or soft soil, they're not so good, and actually they can sometimes increase the vibrations during an earthquake and cause more damage than if the building was just a fixed base building. Many countries employ this method it's a pretty common method. China, Armenia, Japan, Indonesia, United States, the list just goes on and on. The next topic I'd like to cover is shear walls, or structural walls. Basically, these are just stiff walls built into the building. Most buildings actually already are fitted with shear walls when they're built. So it's a pretty basic method, but yet it's still effective. The walls just maintain the stiffness of the building. They're very good at maintaining stiffness of multiple floors also, so that the walls stay square. And they're generally made of concrete or timber. One variation of the shear wall is known as the Muto stiffened wall, and as David J. Dowrick states, this is a precast panel designed to fit between adjacent pairs of columns and beams of moment-resisting steel frames. The panel is divided into slits into a group of vertical ductile beam elements connected by horizontal ductile beams at the top and the bottom. So basically it's just a precast concrete wall. It has slits in it, and it fits right into the frame of your building, and it's very effective at stiffening the walls and making sure that they do not topple or crack or anything during an earthquake. The final topic I'd like to discuss today is fluid viscous dampers, or sometimes just fluid dampers, viscous dampers, any combination of that pretty much. This device has been around for quite a long time. The military has been using them as shock isolators. During the Cold War, they were used to protect missile silos and ships from nuclear explosions. When this technology, which we had years of research on thanks to the military, moved to the civilian market, they became used as shocks in cars. I'm sure you guys use them every day when you're driving to work. But also the transition to buildings was quite a simple one also, thanks to all the research from the military. A viscous damper basically is a device that suppresses structural vibrations by converting the kinetic energy of a building into heat energy. I have here a picture of a viscous damper, actually two of them. This is in a parking garage, and I've outlined it so you can see it a little bit better. Basically, it's a piston system, and so here we have a rod, and the piston, when the building vibrates, this piston moves up into the rod through silicone oil, which is non-flammable, non-toxic, inert, and stable for a long time, which means low maintenance costs. The pressure force of the piston moving through the oil causes only heat as a result. It changes the kinetic energy into heat. These dampers can easily be built into the frame of the building, and then you can hide them behind a wall, which makes them ideal for seismic design. They can also, one example is on the roof of a Pacific Northwest baseball stadium. They were used on the outside of the structure actually, just to help with wind loads and also seismic design, to help keep the roof stable. Also, sometimes they're used in the corners of buildings just to keep the square, or they can be used between parallel walls to help keep the walls parallel also during seismic activity. They can even be installed between the building foundation and rubber-bearing base isolators for extra seismic protection. Viscous dampers work where base isolators don't. So in that softer sandy soil where the base isolators don't work very well, you can use viscous dampers. And also, viscous dampers are ideal for tall buildings because they can be used on every floor of the building, and they're easily hid, and they help the whole building stay nice and square where it needs to be square and parallel where it needs to be parallel. The main disadvantage of fluid viscous dampers is the heat that it creates during seismic activity. If there's too much heat, obviously it can damage the structure around it. Also, over time, this heat can damage the damper itself, which could eventually lead to failure. And especially when dampers are built into the skeleton of a building, behind walls, it's hard to know when these dampers are getting close to failure. So it can get a little dangerous after a little bit of time. If they need to be serviced or replaced, obviously you're going to have to tear out a couple walls to get to these. But because they have the ability to reduce both stress and deflection in the structure, they are one of the most effective seismic suppressors on the market. And so, in conclusion, we can see that all three of these methods are fairly effective methods. They're all low cost, relatively easy to maintain, and they're all long-lasting. Base isolators and fluid viscous dampers can be retrofitted in a building, and also shear walls are pretty much built into every building, so you don't have to really worry about retrofitting those. I would recommend any of these types of seismic suppressors, depending on the circumstances, of course. Dampers are perfect for skyscrapers. Base isolators are good for large buildings such as office buildings, warehouses, schools, things like that. And shear walls are perfect for smaller buildings such as homes or possibly larger buildings, smaller schools, smaller office buildings, things like that. And that is the end of my report. Thank you for your time.